Hello, and welcome to the TMS Innovation Impact Report webinar. Thank you for joining us. I'm Ross Brindle, the moderator for this webinar. This webinar is being conducted by TMS, the Minerals, Metals, and Materials Society. TMS is a professional society of 11,000 members, mostly scientists and engineers working in materials and manufacturing. TMS's members represent industry, academia, and government, with more than half of TMS members coming from industry. This webinar presents the results of a 2-year project performed by TMS through the TMS Energy Initiative, which supports effective energy solutions based on the innovative development and use of materials. You can learn more about the TMS Energy Initiative at energy.tms.org. The project was performed at the request of the U.S. Department of Energy's Advanced Manufacturing Office and Oak Ridge National Laboratory, and was conducted in cooperation with ASM International and the Energy Materials Initiative. The webinar will feature 3 speakers who will provide an overview of the project and its key results. First, Dr. Diron Apelian, Director of the Metal Processing Institute at WPI, will speak to you about the big picture need for this work and the first phase of the project, the Energy Materials Blue Ribbon Panel. This panel set the strategic vision for the project, and Diron was its chair. Then Dr. Warren Hunt, Executive Director of TMS, will provide more information regarding the overall project and the potential impact on energy, emissions, and the economy for the United States. After Warren, Dr. George Spanos, Technical Director at TMS, will discuss important ways that materials and manufacturing innovations can be accelerated for larger impacts that happen sooner. George led one of 5 innovation impact teams that TMS formed to produce the Innovation Impact Report. Once the speakers are finished, we should have plenty of time for questions and answers. You can submit questions via the webinar chat box interface, should be on the far right hand of your screen. I will pose questions to the panel. I'll try to get to as many as I can within the time that permits. We will end the webinar at or before 1 p.m. Eastern. So with that, I'd like to turn the floor over to Diron Apelian to speak to us about national needs and the Energy Materials Blue Ribbon Panel. Diron, it's all yours.
Thank you, Ross, and welcome to this webinar, and appreciate taking the time for you to be with us, and look forward to the Q&A session as well. I think, as Ross said, what I'd like to do is set the context as to what the Blue Ribbon Panel did and the reason or the raison d'etre for this work, which is so critical and pivotal to our nation as well as the world. If we look at our history of our civilization, if we look at the way history has defined our civilization on this planet Earth, you will see that we have gone from a Stone Age all the way to the molecular age. And I don't want to spend too much time on this, but it is, the message here is that materials and material science and materials engineering are so critical and important for the function of our society and the functioning of our society. If we look at the population growth and the rate at which it's growing at 1.4% average per year, and the increase in energy demands at 1.7% per year, it is very clear that the clean energy age is here, and we need to position ourselves as a nation, to position ourselves as a competitive nation, to ensure that we can produce and manufacture and make available the materials for an age where renewable energy has to be a main player. As I said, it's really critical to our national priority. There have been a lot of reports that have been coming out in the recent past that are also pointing out of the critical role of materials. But more than just materials development, it's the manufacturing and making of all of these various materials for the clean energy economy. TMS, the Minerals, Metals, and Materials Society, has led a 2-year study. This was not a committee of 6 or 7 people coming together, but a long-term, many people involved. To do what? to assess the potential of MSE breakthroughs. What are the main areas in which we can really make an impact in short term as well as longer term. Short term meaning next 10 to 15 years, and longer term meaning 20 to 30 years or so. So TMS has really taken the lead to organize and facilitate and, as I said, led this study. And as I've already pointed out, it was not a small committee, but rather many people were involved. Warren Hunt later on will talk about the process and the various phases, but in a nutshell, we had a blue ribbon panel that looked at setting the vision, the framework for what are the areas in which we must be focusing over the next in this study to make an impact, to meet the objectives of the study. And many experts were involved in the various phases of the study, as you can see, from the federal government, national labs, from universities, from corporations, and this is just a small list. As you can see, it was very broad-based. It represented many sectors of the marketplace, if you will, of manufacturing, as well as those companies and researchers that are involved in R&D in this arena. So it was a large contingency of experts coming together and working together collaboratively. With respect to the blue ribbon panel that I had the privilege to chair, there's some wonderful looking folks there in this slide. I don't know where they got the black and white shots from, but there they are. 21 of us met in Seattle a couple years ago, but before that, a lot of work by telecons and reading and assignments. And as it says there, the goal was to identify the areas of the energy sector where the breakthroughs in materials and manufacturing are going to have the largest impact. Impact on what? On addressing the U.S. energy carbon reduction and economic development. The output of this is a vision report that if you have not read it, you really should. It's only about 20 pages or so long, very well written, very well done. A lot of work has gone into it and really set the stage for all the various phases that followed suit. At this point, I'm going to give the floor over to Warren, who's going to talk more about the various phases and what came out of these studies. Warren?
Thank you, Duran. I'd like to first provide you with a little bit of an overview of the project, and then I'll discuss some of the specific findings in a bit more detail. The result of the work that Duran described was a series of reports that were published over the 2-year period of the study. The first of those that Duran referred to earlier was the vision report of the Energy Materials Blue Ribbon Panel. And this was work that identified the high-level areas of the U.S. energy sector where material science and engineering research in particular could make potentially significant contributions to our energy and carbon reduction needs. At the conclusion of the vision report and the Blue Ribbon Panel activity, we convened a number of groups to work on the second phase of the project, in which opportunity areas in material science and engineering that would create these significant economic impact, energy savings, and carbon emission reductions were identified. The results of that phase of the project were published in a report called the Opportunity Analysis for Material Science and Engineering. This report was published at the beginning of 2011. In particular, today what we're going to be talking about is the third phase of the study. This third phase is captured in the Innovation Impact Report, which was just released at the end of 2011, results from the work of a number of experts, 50 or so in number, from representing industry, academia, government laboratories, government agencies. They were organized into 5 innovation impact teams, and the purpose of that group's work was to really look at specific opportunities where manufacturing and materials innovation could deliver the objectives, deliver the opportunities in the relatively nearer term, in the 2 to 10-year period. This report's quite extensive, has been just recently published. It's about 120 pages in length. It also, in this report, in addition to identifying the key opportunities, outlined the key research priorities, which should be undertaken over the next 2 to 10-year time period to realize the opportunities. To present the key findings of all 3 of these reports in a clear and cohesive manner, TMS also developed a summary booklet, which we've called Materials, Foundation for the Clean Energy Age, the large cover that you see on the right-hand side of your screen. And this was recently released. This summary shows how the project's findings can contribute to a strong, vibrant, and progressive manufacturing economy. As you'll note, all of these reports are available on the TMS Energy website, which is, again, accessible at energy.tms.org. If we look at the next slide, you might ask, what's the impact of all these improvements? And this is really a key aspect of the work that was carried out. We identified in the report 54 breakthrough opportunities in the areas of materials development, manufacturing development, processing development. And those 54 opportunities collectively, when all tallied up, if they were able to be realized in the next 2 to 10-year time period, could save more than 2,800 trillion British thermal units. You might want some perspective on that number. And that number is more than the total amount of the U.S. energy provided by wind, solar, biomass waste, and geothermal combined. So very significant. In addition, those opportunities, if realized, could avoid 435 million metric tons of carbon dioxide emissions, which is equivalent to about 1/3 of all the CO2 emissions generated by the U.S. industrial sector. Again, a very significant opportunity. And lastly, but not least, the elimination of $65 billion in unproductive energy expenditures should we realize those opportunities. Now, I've just provided the very highest level information from the report. In the report itself, there are some more specific breakdowns of energy savings, carbon reduction, and economic development opportunity by various areas of energy generation, energy storage, and energy use. So I would refer you to the report for that further information. Now I'd like to talk through a few of the areas where breakthrough opportunities were identified in the project. And I would like to offer them to you in 4 major categories. I'll actually talk about the first 3, and then I'll hand off to Dr. George Spanos to talk about the 4th. And these 4 major areas are listed here. First of all, materials and manufacturing advancements can make manufacturing more energy efficient, more productive, and more profitable by reducing the losses that occur in terms of time, materials, and energy in those processes. So we'll talk a little bit about that. Next, we want to talk a bit about reinventing energy-efficient transportation. And in this area, we talk not only about automotive transportation, but also the many other forms of transportation. And we'll be looking here not only to look at how we might reduce energy and environmental impact, but also jumpstart the development and growth of new supporting industries. The third area that I'll talk about is making the most of our energy resources, both through more efficient energy generation and by maximizing the value of our emerging energy resources. And then last will be discussed the acceleration of innovation, and in particular here the employing of cutting-edge computational tools and techniques that save time and money in bringing the next generation of energy materials and processing discoveries to market. So let me now say a few words about each of the first 3 areas. First, let me talk a little bit about making manufacturing more efficient, profitable, and productive. This is an area of great opportunity for the material science and engineering community. And in particular, materials and manufacturing advances allow us to minimize wasted material through things such as net-shape processing, combining and streamlining processing steps. And an example we'll talk about here in just a minute is perhaps an area like additive manufacturing. And then also, recycling and recovery of both materials and energy can help make manufacturing processes more efficient, productive, and profitable. So these are some of the broad areas. Again, the report in its various opportunities discusses some specific areas in more detail. But let me just mention one particular example of how materials processing can be used to make manufacturing more efficient. And this is an example that is cited in the Materials Foundation for the Clean Energy Age booklet. and it is provided to us by Caterpillar. It's the Caterpillar remanufacturing process. Through a surface modification process that Caterpillar uses to apply wear and corrosion resistance coatings by processes such as metal spray and laser cladding, they were able to remanufacture 100 engines per day using only 10% of the energy that it would take to manufacture new engines. So significant savings in energy, reduction in carbon dioxide, and improvement in manufacturing efficiency. A side note on this area is that Caterpillar offers remanufactured engines to customers at a percentage of the cost of the new ones. And they've also been able to add 3,500 employees to this side of their business, so a clear economic development aspect as well. Let me move on now to the next area that I'd like to focus on, and that's particularly looking at reinventing energy-efficient transportation. And this is an area that there's great opportunity, again, for material science and engineering to contribute. Materials and manufacturing advances can enable us to produce more cost-effective, lightweight, high-strength materials. Reducing the light of our transportation vehicles is a significant way to reduce their energy consumption. Also, it can facilitate multi-material construction of these vehicles. Oftentimes, not just one material of construction is desired for the most efficient structure, but joining these materials together can oftentimes be a barrier. So facilitating construction of vehicles made from many materials is important. And certainly improving battery performance and affordability in hybrid and electric vehicles is important as well. But again, in the way of illustrating something specific for you here, let me just highlight one particular case study that again is described in the Materials Foundation for the Clean Energy Age booklet. And this is from the Ford Motor Company. They have actually been working on developing aluminum castings, aluminum engine castings that will significantly save weight. And they've been able to reduce the product and process development time very significantly and save a significant number of dollars in terms of R&D expense. So this is an area where now again the tools, computational tools and capabilities can really make a strong contribution. And we'll hear more about that in just a little bit. The third area that I'd like to cover is making the most of our energy resources through more efficient energy generation and by maximizing the value of emerging energy resources within the spectrum of energy generation and storage technologies. A few of the kinds of opportunities that were identified in the report and are covered here are converting waste heat to electricity more efficiently, particularly through improved thermoelectric materials. Second was improving the tolerance to extreme operating conditions of next generation energy systems, in particular operating those systems at higher temperatures. And that applies to both conventional power generation as well as the nuclear power generation area. And the third area that falls into this category is increasing the performance of renewable energy systems, such as battery systems. And that's an area where I'd just like to offer one additional example. This is a company called A123. They're a battery manufacturer. Through material science improvements, particularly in the area of the lithium-ion cathode development, in which they have chemically doped this with a nanoscale phosphate to improve battery life, they were able to achieve a battery life improvement of nearly 10 times compared to conventional batteries. That's a significant benefit for the use of these batteries in a number of applications. And again, from the economic development perspective, a point to make here is that this success has enabled the company A123 to grow from a 10-person startup team to over 2,400 employees in 10 years. So we can see that not only do these improvements impact our energy, carbon, and reduction areas, but also enhance economic development. So those are the three examples that I wanted to give you in this area. Let me just make a comment on the next slide as in terms of, well, where is this going forward? How can this all have a material impact? And I think the importance of material science and engineering and energy systems is being really broadly recognized now, much more so. Not only in the federal government, but also in university programs and in industry. But let me just highlight three areas where the federal government has been involved in really moving material science and engineering R&D forward. First, the Department of Energy's Advanced Manufacturing Office, previously known as the Industrial Technologies Program, is focusing on two main areas of technology research and development, innovative manufacturing processes as well as innovative next-generation materials. So this is an area that they're directly supporting, and I think it clearly shows the role that MSE can play. Two relatively recent announcements: the Advanced Manufacturing Partnership. This is the Obama administration's partnership, a national effort bringing together industry, universities, and the federal government to invest in emerging technologies that will create high-quality manufacturing jobs and enhance our global competitiveness. Advanced materials is a key part of this partnership, and in particular, I'd highlight the Materials Genome Initiative, which is being developed through the Advanced Manufacturing Partnership. It's slated as a $100 million multi-stakeholder initiative focusing on accelerating materials discovery and development. And clearly, energy materials have a key focus in this initiative. The Innovation Impact Report will be a valued resource for informing these and other programs as we go forward, because it identifies some specific opportunities for MSE breakthroughs that are going to save energy, reduce emissions, and strengthen the economy. To realize these opportunities in the near term, however, accelerating the materials and manufacturing innovation process is critical. And so to address that, I'd like to hand it over to Dr. George Spanos, the Technical Director of TMS.
So the first question we can ask is, why is accelerating innovation so important? Well, material science and engineering development and deployment historically is often very slow and expensive, and that causes many applications to make do with the existing materials and technologies that are available. But using existing technologies prevents energy systems from achieving their optimal performance, and in particular, these long lag times inhibit the U.S. from being the first to capitalize on the innovation opportunities. We have cutting-edge computational tools and techniques that can provide options for accelerating this innovation. In particular, these tools are critical to understanding the nature of materials and simulating their system performance, and also for predicting a prevention of materials failures. I'd now like to cover two of the tools the material science and engineering community is using to successfully accelerate innovation. The first thing I'd like to discuss is collaborative materials databases. What do they contain? They contain images, sometimes videos, and especially quantitative data that characterize the structure and the properties of materials. For example, the internal structure of a material, its strength, its corrosion resistance. These databases help scientists to make informed decisions when they're selecting materials for a given application. They also streamline the design, reducing trial and error and resulting in large cost and time savings and energy savings. Just as importantly, they provide critical communication with the computational models for both the model input, oftentimes that's experimental input that drives the models forward and validates them, and output so that people can see the output and use the output of the predictive models. There's a great future potential here for this technology. 20 years ago, for instance, structural information about materials was predominantly two-dimensional in nature. But today we have four-dimensional data. And what we mean by that is data that's spatially in 3 dimensions, but also changes over time, and time is that 4th dimension. The growing amount of the 3D and 4D data will continue to increase, enabling the acceleration of material science and engineering advances as we go forward. Another modeling tool, another enabling tool for accelerating materials and manufacturing innovations is something called integrated computational materials engineering. This integrates materials information that is captured in computational tools with engineering product performance analysis and manufacturing process simulations, as brought out by the 2008 National Academy's study on ICME. So the purpose is to simulate the complete materials and component development process from the basic materials issues to simulating manufacturing processes. In this way, it's very useful to reduce the number of physical test models needed, and then this can result in large cost, time, and energy savings. In this regard, one case study that I'd like to mention is a study by Questech Incorporated, which is a materials development firm. They used integrated computational materials engineering to develop new high-strength steels, reducing the development time with only 5 prototypes being needed, saving an estimated $50 million in the development costs. This ultra-high strength steel offers superior corrosion resistance and is ideal for meeting the demanding performance requirements of landing gear in aircraft. Implementing acceleration tools is key, and there are 2 initiatives that are helping to facilitate this implementation. One is the Materials Genome Initiative, and the other is Materials Innovation at TMS. Warren Hunt described a bit earlier the Materials Genome Initiative for Global Competitiveness, and it's a national initiative that supports the development of computational tools, software, new methods for material characterization, and the development of open databases. This initiative is clear recognition by the administration that tools like integrated computational materials engineering and collaborative materials databases are critical to making the process of advanced materials discovery and development faster and less expensive. As visible in the graphic on the upper right-hand side of the screen, in addition to clean energy, this initiative has the ability to impact national security, human welfare, and the next generation workforce. It recognizes the importance, especially of advanced material systems, to solving pressing national energy challenges and effectively promoting a renaissance of American manufacturing. The other initiative I'd like to mention is it's a TMS initiative known as Materials Innovation at TMS. And the purpose of this initiative is to assist industry in the implementation of integrated computational materials engineering principles and techniques. This initiative serves as an interface for cooperative learning, information exchange, and access to resources that are needed to realize the promise of this ICME approach. Details of the initiative can be found at materialsinnovation.tms.org. I'd like to now turn it back to Warren Hunt to wrap up the presentation.
Thank you, George. The materials and manufacturing opportunities we've discussed today form the foundation of a new era of environmental sustainability and economic growth in the United States, fueled by significant cost, production, and energy efficiencies, and global leadership in the manufacture of products and technologies responsible for these efficiencies. Capturing these opportunities requires a systems approach and a cooperative effort. And specifically, we think it needs the following items. First, an integrated approach that engages all facets of the materials and manufacturing spectrum across the academic, industry, and government sectors, and across industry large and small. It also needs rational, sustained federal support for materials-based research and development. We also need to have workforce development in materials science and engineering, not only at the university level and creating the future workforce, but also in the roles of professional society and industry to train the current workforce. In addition, greater industry access to the knowledge, expertise, and cutting-edge resources available through academia and U.S. national laboratories would be a great enabler. There's increased progress in this area. So in summary, material science and engineering clearly has the potential to make great impacts in the U.S. energy, carbon reduction, and economic development needs. And the opportunities are pervasive across many industries and sectors and achievable in the nearer term. In conclusion, materials are indeed the foundation of the clean energy age. Now I'll pass it back to our moderator, Ross Brindle.
Thanks, Warren, and thanks to Diron and George also for your remarks. For those listening in through the webinar, in the right-hand side of your screen, there's a box where you can submit questions. Many of you have already done so as the presentation was being conducted. We have about 30 minutes here for additional Q&A. The way that this process will work is that if you have a question, please do type it into that question box and submit it, and it will come to me, and I'll pose the questions to the panelists. To get us started, I'll choose from some of the questions we've already seen here. I'm not sure if this is a question for Warren or perhaps for Diron. The first question is about the timeline for achieving the opportunities identified by the project. I think it was Warren who presented some statistics for energy savings, et cetera. When can we expect to see those impacts be realized by the United States?
I can take that one, Diron. So I think what we really tried to focus on in this work was the kinds of nearer-term opportunities that might exist. And as I mentioned in some of my earlier remarks, we're looking for opportunities that could be commercially ready in the 2 to 10-year time period. By commercial readiness, of course, we don't mean that they're necessarily fully implemented or that they're fully realizing the benefits, because that, of course, is the role of industry to actually do that implementation. But reducing the barriers to commercial implementation by creating commercially ready technologies was the objective. And so these types of improvements that we talked about, we hope could be realized certainly within the next decade or two.
Well said, Warren.
Great. Thanks, Warren. Thanks, Diron. And then also related to the impacts that we're talking about, a question here that says, how do you know that these opportunities will have this level of impact? Can you give more insight into how those figures were derived and the process that you used to estimate those impacts?
Sure. Let me try that one as well. This is Warren. We engaged the assistance of an organization called Energetics, which does quite a bit of energy analysis for projects of this type. And as part of the work, the experts that we had, the material science and engineering experts, helped us try to quantify what are the kinds of improvements that they could see in a materials property or in a manufacturing process or another area such as that. They're not so much the energy experts as they are the material science and engineering experts. And what Energetics did was, using those projections along with historical rates of progress and conservative projections of future market improvements, they calculated the potential energy emissions and cost savings for affected markets. And as I mentioned in my comments, they made those calculations on fairly broad market sectors. I guess I'd maybe mention that that's important, because many of the kinds of materials improvements we talked about are actually complementary. And so to say any one particular material or process improvement would result in a certain improvement in, let's say, fuel efficiency in an automotive structure, maybe would be too simplistic. Actually, we need to bring all those together. But collectively, they help to analyze what those kinds of opportunities might be.
Great. Thank you, Warren. Another question that just came into my chat box here asks if you can talk more, and I think maybe this is a question for Diron, although the others may have thoughts here. Can you talk more about the additive manufacturing innovation and how that process works and how parts can be made more in a net shape way so that finishing is greatly minimized or eliminated? Can you just give us a little bit more of a sense for how additive manufacturing works? Diron, do you want to take a shot at that question?
Well, I mean, I don't know how much background is required here, but in terms of additive manufacturing, we've come a long way from in the last 2 decades from computer-aided design to having digital data transferred so quickly from one part of the world to the other. Now we're at an age whereby we can take the digital information and actually manufacture a part very much like you print a piece of paper in your laser printer. The paper goes in and you're adding layers of ink where you have designated the pixels to go into. In a similar pattern, excuse the Freudian slip there, you can manufacture components layer by layer by layer in an additive. That's where the word additive comes from. But in terms of the impact of this and the windows to when it's already being done, as you probably know, in many segments of our of the marketplace, from biomaterials to dental appliances, from one side of the health industry all the way to the other side of the spectrum to components that need to be rapid prototyped and manufactured. But I think the big impact and the big opportunities in additive manufacturing are to make structures and components in ways that we cannot make today or at present, at the atomistic level. Some of the work that is being carried out at Lawrence Livermore National Laboratories, for example, by the group there, as well as in other laboratories around the country, and many corporations such as Veritas in New England and others are really leading the pathway here in terms of how to make components and structures and as well properties and performance of these components in ways that are unimaginable at present. I'm not sure how much more detail is needed, but that's what we're talking about with respect to additive manufacturing. But from the context of what Warren presented, we really are talking about an advanced manufacturing, a very competitive, to put us in a competitive, healthy competitive position as a nation. This will enable not only cost-effective manufacturing, but also allow us or enable us to make things that cannot be made at the present.
Thank you, Duran. Excellent overview of additive manufacturing. Another question, a specific question here, asks about A123 systems. I think, Warren, you had a slide where you talked about A123 and their success in extending battery lifetime. Do you happen to know, you may not, but do you know whether the technology that was envisioned in that case study has been commercialized by A123, or is it still in development?
I can jump in, Warren, if you want. It is very much commercialized, from small batteries to very large batteries. In fact, A123 is the provider of the lithium-ion batteries, I believe, to Chrysler, to the Chrysler fleet, and as well as other corporations. So it is very much in the commercial arena, and one doesn't go from 10 people to, what was it, number 2,400 employees, unless you have a commercial sector. It is very competitive, however, and that's why it is important that our manufacturing science and our manufacturing prowess is invested in and advanced, because we're not the only smart people in the world, and there are many other people out there who are trying to figure it out how to make it more cost effectively and quicker and faster. But it is very much a commercial entity.
Thanks, Duran. And I also know that there's more information on this particular case study and several of the other case studies that were mentioned during the webinar in the Innovation Impact Brochure, which people can find at energy.tms.org if you're interested in seeing the results. Also, someone asked a question about whether the slides here will be posted on that same website. The answer to that question is yes. There are a couple of questions, several actually, here about how to keep people engaged and interested. One questioner asks how we maintain the interest and commitment from industry in keeping strong industrial engagement in this activity. Another questioner asks about funding organizations and how we can engage those agencies in this activity. And a third question asks, how do we engage the educational community, universities and faculty, to ensure that the next generation of students will have the skills needed to participate in the innovations and deliver the innovations that we've talked about in this webinar. So a broad question, maybe I'll just pose it to each of you to offer your thoughts on how we can engage industry, funding agencies, and the educational world to continue to realize the impacts that we've talked about in this study. I don't know, George, you've been quiet. Do you have any thoughts to start the reaction to that question?
Sure, that's a great point. In some papers I've written, actually, it's critical to make this kind of thing work, these innovations, to engage all three groups and get them to work together. That is, government agencies, academia and industry. It's absolutely crucial because the problems are just too big for any one organization to make that happen. And in particular, I think this is the role where professional societies really play a big role. And we've done things such as organizing Materials Genome Initiative scoping session at the last conference, Material Science and Technology Conference, where we had people from many different societies. Industrial, we had pretty much an equal mix from industry, academia, and government agencies, and they really have to cross-talk so that we can find solutions to this together. The other thing I'll add is we're working with the University Materials Council on the education side. They have put as a priority integrated computational materials engineering, so we're disseminating information through them as well for these innovation tools that can impact energy reductions and CO2 reductions greatly. I don't know, Warren, do you have something else to add?
Yeah, I mean, I think George gave some excellent specific examples of areas that are underway. I think the general answer I would have to the broad question that you posed, Ross, of how do we engage industry, academia, and others in the process, is that's really the role that professional societies fill here, and that we view ourselves as the kinds of organizations that are neutral third parties that can bring together those kinds of groups. So certainly TMS has as one of its strategic objectives to continue to convene activities like the study that we've done here, as well as through our meetings and our publications, to bring the community together, to disseminate information about funding opportunities, for example. Those things are all roles that we play, and hopefully can to try to do an effective job in cooperation with the various sectors.
Ross, if I could jump in here, because the question that you posed from the person who posed that, it's actually several questions into that one question. And I don't want to be contrarian or disagree with what Warren and George have said. They're absolutely correct in terms of the role of professional societies. But what I'd like to add to this conversation, and I think it's a very important conversation, a crucial conversation that we have to be having, is that every one of us, it's not that a professional society is going to do this. You just sit back and relax and somebody else is going to do it. Wrong. We have to take every one of us. If there's one message in this webinar, is that every one of us is empowered. Every one of us has a responsibility to be an advocate for not only our society, materials engineering, or material science and engineering, but really we have to be advocates for technology, investments in R&D, and to really have the fuel that makes this engine really function to be continued. So every one of us has to be advocates. Every one of us has to be involved and engaged. And if we think that, this whole exercise is just about getting some funding to be available to do R&D, we miss the point. The idea is to energize, to catalyze, to revitalize, and to bring our consciousness and our legislators and the people who actually make these investments in R&D to be aware of the lost opportunities if we do not do it. So I think, in addition to professional societies, every one of us has a responsibility. With respect to higher education, we cannot be in denial. We do have an issue. 4.5% of high school graduates in America are going into engineering, whereas it's 11% in Germany and it's 21% in China. So with respect to STEM education, we have a challenge here in the U.S. to ensure that we get some of the best minds and the brightest and the best to come into engineering, so that they can participate in this dialogue, and more than participate, contribute to the advancements of our nation. So, those are some of the challenges that we have. But I think in addition to higher education, it's community colleges, STEM education, and the workforce that needs to be available and ready to contribute with all of these wonderful visions that we have and the opportunities that we see.
Great. Thanks to all three of you for your answers to a complicated multi-question there. Another question coming in from the audience. I think this is a question for you, George. It's about collaborative databases and acceleration. The question reads, in order to maximize the effectiveness of our materials modeling and simulation, we need to access data, and the Materials Genome Initiative, for example, is seeking to grow databases to provide that kind of access to data. And it's just kind of a general question. How do you see this working or being handled? There's competitive issues, export control constraints, and other barriers to sharing that kind of information. Can you give a little bit more insight into how we see that collaborative databases acceleration potential actually occurring?
Sure, Ross. That's an excellent question. In fact, in the Materials Genome Initiative paper, it describes the materials innovation infrastructure, and a key element is the digital data. In particular, this is something that is mentioned. This issue is actually mentioned in the Materials Genome Initiative paper, and it is something that we're dealing with. The idea is that paper recommends, the Materials Genome Initiative recommends as much as possible open access to digital data. This, of course, proprietary issues come into play, but the pre-competitive stage is where we really want to attack this, where people can work together and leverage in terms of digital data. And we call this material cyber infrastructure oftentimes, where we have to link up databases and give a lot of people access to it. It's one of the key components of the Materials Genome Initiative. And I know that a number of organizations are working on this. TMS is involved in working on workshops and such in this regard, as are other professional societies. So it indeed is a critical issue, and I think we just have to get people together at the pre-competitive stage and develop these open access databases as much as we can. Thanks,
George. Another kind of interesting question here. I think it's a little bit of a tough question, but I'm going to pose it to the panel anyway. It asks, when do we take an overarching economic analysis and start looking at engineering versus science? Are there engineering limits that tell us where not to go or where not to focus our efforts? And I know that question of where will impact occur and where will impact not less likely occur was one that the Blue Ribbon panel wrestled with in particular. So I don't know, Duran, if you have specific thoughts to how we can use material science and engineering limits to direct our efforts by saying where we will not focus our research efforts. Any responses to that question, Duran?
I'm thinking.
It's a tough one.
I think it's a very important question, though, but I think the Blue Ribbon panel actually did carry that out, where the analysis was carried out in this way, where we looked at where the needs are in terms of a societal needs, as well as the impact that we can make in the short term. I may have said this earlier, in the first, next 2 to 10, 15 years, as well as longer term. And the thing is that it's not all black and white. I mean, the engineering analysis points out as to what can be done, but also they work collaboratively with the science, because the science enables certain technologies to be developed, but also engineering advances also point out the kinds of science needs as well. So there's a play between engineering and science in that sense. But I think that the analysis that was carried out, as well articulated in the Blue Ribbon panel report, has the results of that analysis over a period of short-term and long-term in terms of where the major breakthroughs are. Anything you can add to that, Warren or George?
This is Warren. I'll maybe just make one quick comment and then pass it over to George. Is, part of the reason that we selected the teams that we did for this study was to really try to get both a broad engineering and science perspective. So we included, a strong component of experts from the industrial sector who, I think, bring that economic reality with them to the table, in addition to the folks who could contribute the science from the academic and national lab perspectives. And so yeah, I think that we would say that we hopefully integrated that thinking into looking at the 2 to 10 year opportunities, and especially with the industrial representatives there, saying what are the kinds of things that really are realistic, not only from a technical and scientific perspective, but might also be possible from a implementation and an economic perspective as well.
Yeah, I'd like to add something. This is George. More specifically, when we go forward with these innovations, particularly integrated computational materials engineering, if we remember, it's materials information captured in conjunction with engineering product performance analysis and manufacturing simulations. And what that does in that optimization process is it takes into account upstream the limitations due to engineering and manufacturing, such that certain materials are ruled out in the early stages or not ruled out in different directions or determine where to go. So sort of on a more quantitative basis, that's how we handle looking at the constraints of engineering and manufacturing on the materials development process.
Great, thank you very much. We have my clock says we have about 5 minutes left in this webinar, so if you have a question we haven't yet answered, please submit it.
Russ, I received I received an email from a colleague of mine. I'm not going to identify the person nor the professional society, but actually it's a relevant one. This gentleman is a director of another professional society, and he is suggesting that there's an opportunity and room with respect to databases, with respect to materials genome, to have a much more collaborative relationship and activity between all the various professional societies, because there's a lot of data in various different pockets. And I think it's a good point, and I know that the leadership at TMS certainly has that in mind. If I can speak for the leadership of TMS, at least when I've been involved in it, and I think it continues to do so, where it's a collaborative spirit that underlies our organization at TMS. So I think there's an opportunity for various professional societies to work together here with respect to the development as well as the sharing of databases, so that it's integrated and that it's available to many people to help the community.
Thank you very much, Duran.
Yeah, I sort of asked the question and answered it. So.
Yeah, no, that's good. Given the time, I think I'll just pose one final question to, I think it's a question to Warren. What are the next steps here for TMS and for the broader community?
So I think what we've tried to do over the last couple of years in this project is to identify with the community's input where these opportunities are. We're now in the process through this webinar and other activities as well to try to communicate those opportunities to both the stakeholder groups and the public at large, to try to both really move things forward quite a bit more if we can. So we're really at a stage now of really communicating the results and trying to carry that forward. We certainly think, some of the areas that have been brought up today, that there are great opportunities for us to work more together on things like collaborative databases, on things like foundational engineering problems. George mentioned around the Materials Genome Initiative, not only clean energy, but there are national security issues and health issues and so forth that will fit there. So I think we're going to see, I think it's a really exciting time for the materials science and engineering community. The fact that we can bring these materials development and manufacturing acceleration tools to the party to really address some of the significant problems we have, and to really be key players now, right up there with the design engineers and the manufacturing engineers in very focused and real-time solutions to the problems that we have. So that will be, I think, a next step for our community in both through the work that TMS does to try to bring the community together, but I think at large.
Very good.
Thank you, Warren, very much. I think this will conclude the webinar. I want to thank Duran, Warren, and George for your prepared remarks and for your insightful answers to the questions. I want to thank all of the participants for interesting questions, thoughtful questions. I think there's a lot of engagement here and many questions about how do I continue to be involved, how can we influence and disseminate this information to the right people. Those are important questions. If you want to get involved, please visit energy.tms.org. Copies of all of the reports that were talked about are on that website. And if you want further information, there's contact information shown here on your screen. Please do reach out to us. We'd be happy to provide more information if we can. And we look forward to working with the broad material science and engineering community to realize the impacts that we think are possible in the next 2 and 10 years and beyond. Thank you very much for your time, and this ends the webinar. Goodbye.